Hello, everybody. Welcome back to Calculus. So this is section 5.4. Section 5.4 is about triple integrals. All right, so you have been studying double integrals, both in rectangular coordinates and in polar coordinates. Now we get to use three integral signs all at the same time. I hope you're excited. All right, so here come triple integrals. Let's start. All right, so we are now in the fourth section of chapter 5, and we are going to add yet one more dimension to our integration. So now we will be using three integral signs together. All right, now before I go further, I would like to explain something in light of what we have been doing in the past, okay? And so I have talked about this recently, but I do want you to one more time, and hopefully that you will understand where I'm going with this, right? So first, we had a function, and this is what happens in Calculus 1. Remember, I almost always start a lesson on Calculus 3 by going back to Calculus 1. And so if you have a real valued function on the reals, all right, we can talk about the interval a, b, and as we said, as I said before, if you don't integrate anything, okay, if you just say, or the constant function 1, if you just have dx in here, you know what this is? This is b minus a, and this is the length of the interval, right? Okay, so that's like the fundamental thing. Now you could, of course, integrate something, right, in one-dimensional space, which is on the line. If you integrate this, this of course becomes the area of the region under the curve, okay? Now assuming that fx is greater than or equal to 0 on the interval AB, okay? And then we added a dimension, and we talked about double integrals, right? So you have this R, and then we can talk about some surface. You know, this is f of xy, and let's assume it's also non-negative. All right, now if you don't integrate any particular function, but maybe the constant one function, right, so we can write the double integral over R of dA. And so this is something we've talked about recently. This just becomes the area of R. Okay, why is this the area? Well, because actually this is the definition of the area. You know, I mean, how do you define area? Well, here's a precise definition of the area. Okay, you can think of this as remember I talked about this 1 inch thick piece of meat or the steak or something, right? If you have an R cross 1, in other words, R cross the interval 0 to 1, this just becomes a solid of height 1 over the region R, and of course the volume of that in the unit square cubed will be the same as the area of R in units square, right? So this is what we talked about last time, and you can certainly find the area of the region by a double integral, or you can actually integrate some function like the one shown here, right? F of xy, and then you can do dA, and this will be the volume of this solid E. I'm going to call this E, and so E is this solid bounded below by the xy plane over the region R, and the upper bound, it's bounded above by this surface, which is f of xy, right? So this is what we talked about last time. So the question is now, what happens if you have a three-dimensional object? So here's a three-dimensional object, you know, thinking of this as a solid E, and every point x, y, z has a value associated with it, x, y, z, right? And even if you assume that it's non-negative, like in the top here, right? Now, if I take the triple integral, which I will define in a moment, if you take the triple integral and then just do this dv, which will be, as you expect, it's going to be dy, dx, dz, or any kind of permutation of that. Okay, not surprisingly, this will just give you the volume of E, right? So this is very much like the length, and the area and the volume. Okay, and in fact, this is the definition of the volume moving forward. All right, so the question is, what happens if you integrate some function of xyz over E? Okay, so this is where the question comes in. We don't have a good way to understand this, right, in any of the interpretations of this, because after all, I can't even draw a, see over here, I could represent z as the height of the function, so we can talk about this volume, right? So over here, I can't draw a four-dimensional graph of f of x, y, z. So what does it even mean, right? So does it even make sense to integrate in 3 dimensions, right? And that's why I talked about the rod example. Remember the rod example here? Okay, so if you have a stick, okay, and you can think of a stick as a one-dimensional object, and if the density at any point f, x, if the density at any point x is represented by fx, then the integral of fx dx is the mass of this whole stick, right? Because I mean, remember what? What is integration? What is integral? Integral is the continuous version of addition, right? So you are basically adding all of these values. One value is defined. Fx is defined at every point x between a and b. Right? And if you continuously add, which is the integration, right, then you get the total mass of this object, right? Okay, so what happens if you have a part or a subset of the plane, all right? We will use the word lamina, okay? Lamina is sort of like a sheet of paper or a metal sheet or a sheet of something that's made of something, okay? So the